Hi, I'm Farzam, and today I'm going to talk about the metrical task systems problem on general metric spaces. This is based on a joint work with James Lee. So first, let me define the problem. So imagine we're given a metric space, in this case, the path metric, and that we are standing at a point in this metric. Now, at any point in time, a monster appears at some point in this metric, and if it appears at somewhere that we are standing on, we have to make a move, either to the left or to the right here. And if it appears at somewhere that we are not standing on, we don't have to take any actions. And we have to make these decisions online. We don't know what will happen in the future. And we would be paying a total cost of the amount of distance that we have traveled over time. And the goal is to minimize the cost of this online algorithm when compared to an optimal offline algorithm that knows the future. So more precisely, we say that an online algorithm is alpha competitive if for any fixed input sequence until any time t, the cost paid by the algorithm is at most alpha times the cost of the opt. Here we allow some constant additive factor, and this factor can depend on the metric, but the crucial thing is that it cannot depend on, it cannot grow with t. And it's not hard to verify that if we are only allowed to make actions deterministically, we can't hope to get a competitive ratio better than omega n. But if randomness is allowed, we can do much better. So what do I mean by that? So suppose we allow the algorithm to take random actions, and then we're measuring the cost of the algorithm as the expected cost that it's going to pay. And if we do that, we can do much better. We can get down to polylogarithmic factors in n, where n here is the number of points of the metric space. So more generally, the metrical task systems problem is defined as follows. We're given a metric space X and a sequence of cost vectors, non-negative cost vectors, CT, arrive over time. And we have to respond to CT online with a possibly random point XT in X. And the total cost that we're going to pay is the sum of a service cost and a movement cost. The service cost is the entry of this cost vector at the point xt, and that we're playing on. And the movement cost would be the distance that we have traveled, as we saw in the earlier example. And the cost of our algorithm would, of course, be the expected value of this quantity. Equivalently, we can view this problem as one in which we are allowing the algorithm to play a point in the probability simplex on X. So more precisely, suppose that the algorithm is playing at a point mu t in kx, where kx is the probability simplex defined on X. And then the service cost, the expected service cost would be exactly the inner product of CT and mu t. And the movement cost can be described as this earth mover distance between mu t minus 1 and mu t. And so one other way to view this is that we are allowing the algorithm to play a fractional mass on different points in this metric. Yeah, so this problem was introduced in 1992 by Borodin, Lineal, and Sachs. It is one of the central problems in the area of online algorithms. And it has been conjectured that correct bound, the correct competitive bound for this problem is theta of log n. And in fact, for certain metric spaces, it has been proven that we can either do order log n competitive or like an omega log n bound is necessary. But for general metric spaces, the best thing that we know after a long sequence of work is log squared of n as an upper bound, and the best lower bound that we know is log n over log n. Our focus on this talk would be on the side of upper bounds, and so now let me tell you how this upper bound of log n squared is achieved on this problem. So let's first look at a rather simple example of the uniform metric. So a uniform metric is a metric on endpoints in which the distance of any 2 points is exactly the same, say 1. And the first heuristic that comes into mind is that given a class vector, what should probably do is to reduce the mass at point I proportional to the amount of cost that the point I sees. So if some point sees more cost, it makes sense to reduce the mass faster there. So yeah, maybe the first algorithm that comes into mind is, say, define this mu t plus 1 as mu t minus some eta times c, where eta is a learning rate. And of course, there's this issue that we're only decreasing mass here, and we would be leaving the probability simplex if we just did that. So instead, we have to project this point back into the probability simplex. Or in other words, we have to somehow redistribute this removed mass to the other points. And yeah, the first guess might be to do this projection just based on the Euclidean distance. And if we do that, then the algorithm sort of corresponds to the projected gradient descent. Note that in the gradient descent, we are moving by this by the gradient instead of this vector c, but other than that, these algorithms are the same. And but that unfortunately doesn't work. What we can do is something that is kind of a generalization of this. Given a strictly convex function phi, we define this Bregman divergence of 2 points based on phi as is phi of mu minus phi of nu minus the gradient at mu times nu minus mu. And this is always a non-negative quantity, and it follows from convexity of phi. And yeah, if we do this projection based on this Bregman divergence, then what we have is a mirror descent algorithm. And the nice thing about it is that this mirror descent provides us with a sort of the mirror descent framework sort of provides us with a potential function that lets us control the progress of the algorithm. So more precisely, if we do this step with this Bregman divergence as described above, then for any point nu star, this inequality holds. And what this is telling us is that if our algorithm just stays at mu t or mu t plus 1 pays more cost than nu star, then it would get closer to nu star in terms of the Bregman divergence. So the algorithm cannot get cannot pay a more service cost than opt forever. And if there are some certain Lipschitzness and under some mild Lipschitzness conditions, this would allow us to bound the service cost of the algorithm by the total cost that the optimal algorithm is paying. And in fact, this is something very crucial here, because in the earlier work on online algorithms, and in particular in the metrical task systems problem, one of the hardest parts of the analysis was to be able to relate to somehow analyze the behavior of the optimal algorithm to be able to relate the cost of your algorithm to the cost of opt. But here, essentially for a large family of regularizers phi, you would automatically have this property that your algorithm is competitive in terms of its service cost. So the service cost of your algorithm would be a proxy for the cost of opt. And if you can also bound your movement cost by your own service cost, then you would be down. So now the whole problem gets down to choosing the correct regularizer phi. So if we took phi to be phi of mu to be just the normal square root of mu, then what you would end up with is the same as the projected gradient descent. And then the update formula would be given by something like this. Here, lambda I would correspond to the Lagrange multipliers that are essentially keeping you inside the polytope. But let's forget about these terms for the sake of this talk. And so your update would be approximately minus eta times Ci of t. And the issue here is that there's no way that we can relate this value to the cost that the algorithm is paying. And so that is our only proxy for the cost of opt. But if we do something more clever and take phi to be the negative of the Shannon entropy, and mu, which is the sum of mu I log mu I, then the Bregman divergence would turn out to be the relative entropy. And the update rule would look like this. And if we ignore the term lambda, you can see that the amount of mass that is moving at point mu I is approximately mu I times Ci, which is exactly the amount of service cost that we are paying at point Ci, at point I. So we are moving with the same amount of mass that we're moving the same amount of mass as to what we are paying as a cost. And that is very, very convenient. And this is very good. Then we would be able to bound our movement cost by some factor of the service cost. And we already know this is bounded by the service cost of the opt, so we're in good shape. But this regularizer doesn't work yet. It's because, as I mentioned earlier, we also need some Lipschitzness assumptions on phi to be true as well, which is not true in this case. And for that, there is a fix, which is instead of working with the entropy itself, we have to work with this shifted entropy. We shift all the values by some delta, where delta is 1 over n. in here. And our update rules would change and the analysis would become a bit more complicated. But at the end of the day, we can show that this algorithm is log-n competitive. Now, if we were instead working with a more general problem, which is, now suppose instead of working with the uniform metric, we were looking at this problem on the weighted star, which is, so the metric is defined as the shortest path distance between the leaves of a weighted star. So distance between like this vertex V2 and V3 is defined as W2 plus W3, where this is the shortest path between them. And it turns out that with some minor modification to this regularizer, we could still get a log-n competitive algorithm. And what we should do is we should weight this entropy by Wi. So we should weight the term corresponding to mu I by Wi. And what this would do is that it would slow down the updates of mu I by a factor of 1 over Wi, which kind of makes sense because if the weight of some edge is large, you don't want to change that edge fast because otherwise you would be paying a lot of movement cost. And this algorithm is still log-n competitive. Now let's move to a more general family of metric spaces that are called hierarchically separated trees or HSTs. So an HST is basically a rooted weighted tree in which the weight of the edges goes down geometrically along root leaf paths. And then the metric is defined on the set of leaves of this tree. It can be defined as the shortest path distance between those pairs of vertices. And you can see that as the weights go down geometrically here, the length of this shortest path is essentially dominated by the largest weight of an edge in this path. And the interesting fact about HSTs is that they can approximate any metric up to a factor of log-n. So what does that mean? It means that we can randomly embed any given metric into an HST so that the distances do not go down at all. And in expectation, they only go up by a factor of log-n. An implication of this theorem is that if we can find an order alpha competitive algorithm for HSTs, we would then obtain an order alpha times log-n competitive algorithm for any metric by just using a black box reduction to this theorem. And in fact, this is how we do have a bound for general metrics in the prior work. In the work of Bubeck, Cohen, Lee, and Lee, and the work of Koester and Lee, what they actually do is that they provide an ordered log-n competitive algorithm for HST metrics, and then use this theorem to show that any metric, for any metric, you would have an ordered log-n squared competitive algorithm. So perhaps not surprisingly, they obtain this log-n factor using a mere descent algorithm. So instead of directly working on the probability simplex defined on the points of the metric space, which in this case are just the leaves of this HST, they work with a lift of this simplex. So more precisely, they represent the probability distribution on the leaves as a unit flow from the root of this tree to its leaves. So first the root gets to decide how much mass it's going to play on the left subtree and how much on the right subtree. And then the nodes at the second layer get to decide how much of the incoming mass are they going to play on the left and right subtrees, and so on. So it's a step-by-step decisions and decision-making process, sort of. And then given these internal variables f, which represent the flow, if we define this regularizer as follows, it turns out that we would obtain a log n comparative algorithm on these HST metrics. So to make sense of this regularizer, maybe let's first forget about these delta values and also rearrange the terms. So what you would get is essentially a weighted sum of so if you look at this thing, this looks very similar to what we had for the case of the weighted star. So essentially this algorithm is running weighted star on each of these internal nodes kind of separately. But what the variable that is running this on is these ratios FUV over FU. I forgot to tell, so this FU is the incoming flow to U. So since this is a tree, the incoming flow, so the flow just comes from the parent of that node. So the incoming flow to this node is exactly F12, to this node is exactly F511, and so on. And so this ratio, some sort of is the conditional probability of playing on the subtree rooted at V, given that we are playing at the subtree rooted at U. And then the dynamics would look like something like this, and which is also very similar to what we had in the case of weighted star, but now our variables are these ratios. As I alluded to earlier, so the way these prior work handled the case of general metrics is just via simple black box reduction to these HST metrics. And then you would get a log n squared bound, but the conjecture is that we should be able to do log n on any metric. And this extra factor of log n that comes from this black box reduction seems kind of unnecessary. So it seems like mere descent is the correct framework to approach this problem. And as a first step towards getting rid of that log n factor, one might ask whether at least we can get rid of this black box reduction and directly do mere descent on some polytope that is related to our metric and get a comparative algorithm that is log n squared comparative, or even like polylog n comparative. And in fact, this was asked by Ubek. And our main result is that we answer this question positively. And we show that essentially we get the same competitiveness guarantees via purely running a mere descent algorithm on a DAG that is built on top of the given metric X. So what do I mean by that? I'll explain that in a minute. So first, let's look at the path metric again. Suppose we want to embedded into this HSC, where the weight of the edges at this bottom layer is 1, at the top layer is 2, and 4, and 8, and so on. And we can see that although in this HSC, the distance of, for instance, these two vertices is well preserved. I mean, it's 2 in this HSC metric, and it's 1 in the original metric. But on the other hand, the distance between a pair of vertices like these two in the middle is not well preserved at all. It's like 2 to the height of the tree, which is n, where n is the number of nodes here. And so the approximation is far from being correct in the HSC. So, and we want it to be like off by a logarithmic factor at worst. So if, for instance, the adversary made you move a lot of times between these 2 points, by simulating the mirror dynamics on this HSC, you wouldn't get a competitive algorithm because, yeah, because the HSC has a very bad estimate of the correct distance between these two. And so this is why we would need to do this HSC embedding randomly, and we cannot just embed this path metric into a fixed HSC. So here's how we fix it in our results. So we still consider the same kind of dynamics that represents a node at the leaf by a flow from the root to the leaves, and the distribution is determined by these flows. But we kind of modify this tree and add some new edges to it, and so that it wouldn't be a tree anymore, but it will still be a DAG. And now there are multiple ways that to send a flow to any leaf in this tree. For instance, if we take this leaf, for instance, we can send it like this, like that, sorry, like that, like that, or from this path, perhaps. So there are multiple ways to represent a single vertex in this, a single leaf in this DAG. And eventually what we're gonna play is at this leaf is the sum over all these, sum over all incoming flows to this leaf from any path from the source. What we do next is we define this regularizer, which is similar to the previous one, a multi-scale entropic regularizer. And we can define it in the same way. The only difference is that here, FUs are, so previously FU was defined as the incoming flow, which was determined by the flow from the parent to a node. And it is still the case for a node like this one, which has only one incoming edge. But for instance, this node has 2 edges going into it. So F of this node would be the sum of this F36 and F26. And adding these cross edges would allow us to somehow be able to incorporate all reasonable HST embeddings into this DAG while like paying a constant factor approximation. So for instance, to see that the issue that we had earlier doesn't persist anymore. So the issue was for moving a lot between these two nodes. And so if we were representing the flow to the node on the left by this path, then we could simply change it to a flow to the node on the right by deleting the mass on this edge and adding it into this edge on the right. And both of these edges are of weight 1. So the total amount of weight that we are changing here is proportional to the actual distance between these two nodes. So yeah, then the dynamics on this stack would also be defined similarly to the previous one. And what we can show is that this dynamics is log n squared competitive in this metric. Note that it's not log n competitive as it was for the case of HST. So what's the reason? The reason is that by building this stack, we still pay a log n factor in terms of the approximation. Roughly speaking, what happens is that although this stack contains all the necessary, all the like important HST embeddings for this metric, in order for the algorithm to switch between these representations, it will still need to pay a lot of cost, and that is not something that we can bound nicely. And the main technical contribution in our paper is to show that for any metric, constructing such a DAG is possible. For the case of the path metric, it's an easy exercise maybe, but in general, it's much more complicated. And then we show that as long as the number of source sink paths in this DAG is polynomially bounded in the number of points in the metric, then the dynamics is log n competitive. And by putting these two things together, we would obtain that this dynamics on the DAG is log n squared competitive with respect to the original metric. And just to see that this was the case for this DAG, note that the out degree of every node was at most 4 here. Like, there are 4 edges going out, and the height of the tree is around log n, so there are at most 4 to the log n many source sink paths here, which is polynomial in them. And that's it. And as for the open problems, so of course, we do not improve upon this log n squared bound, although we have made some conceptual progress in this problem. And even for the path metric, we can't do better than log n squared. We don't know how to do that. And as for the lower bound, in general, it is still open to improve upon this log n or log n. And it is well known that if you can prove a bound for HST metrics, it would imply a lower bound for all metrics.